What's the first thing you ever learned about black holes? Do a Google search for black holes and I guarantee that you will find this statement. A black hole is an area of such immense gravity that nothing, not even light, can escape from it. It's the first thing people learn about black holes, and it really is everywhere. It's so common, in fact, that it has become received wisdom, passed from person to person, with everybody repeating it but nobody actually questioning it. Is this the first thing you learned about black holes? If nothing else, is this all you know? If so, you're not alone. But why should anybody question it if indeed a black hole is, according to what has become a mantra, an area of space whose gravity is so strong not even light can escape? They should question it because it just happens to be wrong. Okay, not completely wrong, but exceptionally misleading. And to understand why, let's step back a bit. If you dig a little deeper, it's also often said that light cannot escape from a black hole because at the event horizon the escape velocity reaches the speed of light, and because light cannot travel faster than, well, light, then it cannot escape. This is not correct either. All of this leads many people to see gravity as somehow being so strong it pulls a photon back as if it were attached to a rubber band which is stretched to its full extent before the photon can leave the black hole. Gravity therefore acts like some sort of brake on photons attempting to pass through the event horizon into the space beyond, but this is not what happens. There's another piece of received wisdom which says that light only and always travels in straight lines. Unlike the black hole mantra, our own experience, or experiments we might have done at school, dictates that this one is totally correct and can be relied upon. Until, of course, we start talking about gravitational lensing. Here's an illustration of gravitational lensing from the European Space Agency. In this graphic at top left we have a distant pulsar, a type of rotating neutron star. In the centre we have a galaxy, and bottom right we have the Earth. The galaxy is obviously between the pulsar and the Earth. In this interpretation, light leaves the distant pulsar and is deflected by the mass of the galaxy in the middle of the image. Or to be more exact, the galaxy's huge gravity splits the light into two separate paths, meaning that we see two images of the pulsar from the Earth. Now this phenomenon is well observed and understood and gives us such things as Einstein crosses, which consist of multiple images of distant galaxies as shown in the inset at top right. Here we see some of the foreground lensing galaxy which is bending the light from a more distant galaxy into 5 separate images. But wait a moment, light only travels in straight lines, so how can its path be bent by gravity? And so we finally get to the answers to these questions. The path of light is not being bent or deflected by gravity. It can only travel in straight lines, as we said. It's space itself which is curved by gravity, as stated by Einstein. And because the space the light travels through is curved, the light has no option but to follow that curve. It's like a ball in a roulette wheel. It travels in a straight line, but the space in which it's moving is curved, so the ball has no option but to travel in a circular path. The more the mass, the stronger the gravity and the greater the curvature of space. Now, what do you think would happen in a place where the gravity is so strong, space is curved to extremes? That place, of course, is a black hole, where the physical laws we are familiar with are pushed to their limits. Here you have photons inside a black hole. The space they are travelling through has been warped and bent so much by gravity that the photons can only follow circular paths inside the event horizon. From the photon's point of view, it is moving in a straight line, but the curvature of space is so extreme that it leads the photon on a path which means it can never cross the event horizon. And this is the reason light cannot escape from a black hole. It's not directly to do with gravity or escape velocities, it's more a question of geometry, the geometry of extremely curved space-time, which imprisons photons forever inside a black hole. The extreme bending of space can also be seen in this simulation of a black hole by NASA's Goddard Space Flight Center. It must be stressed that all of this simulation is taken directly from Einstein's equations of general relativity and is not just some random guess. The simulation is, as far as it's possible to tell, an accurate depiction of what happens to light around a black hole as a result of the extreme bending of space-time. Seen edge-on, notice that the black hole's accretion disk appears to flow above and below the event horizon. It doesn't, of course. Space is curved so much in the vicinity of the black hole that light is, again, following a curved path, allowing us to see the part of the accretion disk which is behind the black hole. Watch what happens as the simulation changes to a full-on view and back again, and you will see the effect which curved space-time has on the light travelling through it. Another myth about black holes concerns how they consume matter. Supermassive black holes do not, contrary to what many people seem to believe, swallow their host galaxy. Stellar mass black holes do not wander the universe gobbling up everything in their path. This misconception arises from not understanding how gravity works. Let's investigate. Let me ask you a question. Which has the stronger gravity, a star of 10 solar masses or a black hole of 10 solar masses? Just think about that for a moment. The answer, of course, is neither. Their gravitational fields are of exactly the same strength. Why is this? The only factor governing the strength of a gravitational field is the mass of the object. Objects sharing the same mass will always have the same gravity, and it doesn't matter if one of those objects is a black hole, a star, or anything else. The only thing which matters is the amount of mass. Now let's give our 10 solar mass star a few planets. What do you think will happen to those planets if we replace the star with our 10 solar mass black hole? The answer is, of course, nothing. The planets continue in their orbits unaffected, although pretty soon it's going to get very dark and cold on those planets. But the important thing is that they are still orbiting a 10 solar mass body, so the black hole's gravitational effect on the planets will be no different from the stars. They will continue to orbit the black hole as if nothing had happened. Now let's place the black hole at the centre of a galaxy. Its gravitational influence is strong enough to keep planets circling it, but does not extend further. Remember, this is a 10 solar mass black hole which replaced our 10 solar mass star, so its gravity is no stronger than the star's was. It certainly cannot swallow anything further out in the galaxy. In practice, of course, supermassive black holes at the centres of galaxies can be measured in millions or even billions of solar masses, but the idea is the same. The gravity of the black hole has a finite range which depends solely on its mass. This amazing animation from the European Southern Observatory, compiled from 16 years of infrared observations, shows the movement of stars around the supermassive black hole known as Sagittarius A star at the centre of our galaxy. All of the stars in this animation orbit an unseen, compact object with around 4 million times the mass of our Sun. That mass obviously generates a strong gravitational field, but exactly how strong? So here's a question for you. How many stars in total do you think orbit Sagittarius A star? Bear in mind that there are approximately 1,600 stars per cubic light year at the centre of the galaxy, so how many have actually been pulled into orbit around the black hole? I'll give you a second to think about that. The answer is probably not as many as you might suppose. Only a few thousand stars at the centre of the galaxy orbit Sagittarius A star. even with its mass of 4 million suns, a few thousand out of the estimated 200 billion stars in the Milky Way galaxy. Therefore, contrary to popular belief, Sagittarius A star is not going to swallow the galaxy, still less anything beyond our galaxy. Let's zoom in a bit. The bright star moving rapidly here is designated S2. You can see it looping around the black hole, each complete orbit taking 16 Earth years. At closest approach, it moves at a blistering 17 million kilometers per hour and comes to within 17 light hours of the black hole, or 4 times the Earth-Neptune distance. Yet still, Sagittarius A's gravity is not strong enough to swallow it, even though the star passes very, very close to it, astronomically speaking. In fact, we've never seen any stars being consumed by our local supermassive black hole. The stars orbiting it are simply too far away and moving too fast to be consumed, so please can we put the idea that black holes are consumers of galaxies to bed finally. Occasionally, however, the black hole does swallow lumps of material in the swirling accretion disk of matter surrounding it. This results in a bright flare across many wavelengths, infrared, X-ray, radio. The flash you see in the middle of the screen is one of these flares, which is the result of Sagittarius A star consuming a lump or a knot of material which is orbiting it. This allows us to see exactly where the black hole is, but more importantly, it confirms its existence. This animation conclusively, therefore, demonstrates that there really is a dark, compact, massive object at the centre of our galaxy. Related to this, there's another common misconception that our entire galaxy orbits around Sagittarius A star. Clearly, from what we have seen, it does not. Only a few thousand stars out of 200 billion orbit the black hole. Our galaxy orbits around its centre of gravity, which is, quite obviously, the centre of the galaxy, taking 225 million years to rotate once. So let's kill that myth too while we're at it. And this is it. Sagittarius A star, the supermassive black hole at the heart of our galaxy, as imaged by the Event Horizon telescope, a global array of radio dishes which form a virtual telescope the size of the Earth. Swirling around it is the accretion disk. The dark area in the middle is not the black hole itself, but an area around it where there are no photons because any entering that area are immediately pulled in. As Sagittarius A star itself is black because it emits no radiation, as we've seen no photons of any wavelength can escape from inside the event horizon, it's forever invisible, but it's inside that dark area, perhaps occupying 1/10 of its diameter. Well, that brings us to the end of our video about myth-busting black holes. We do hope you've enjoyed it. If you know of any other common black hole myths or misconceptions, we'd be only too happy to address them in a future video. Describe them in the comments, and you can also, of course, ask any questions you may have in the comments too. Do have a look at What is a Black Hole, our video which introduces black holes, and the other videos on the channel, of course. From everybody at Space Oddities, thank you for watching and goodbye.
Welcome to Space Oddities and this edition of An Astronomical Life. Today we're looking at Johannes Kepler, 1571 to 1630. Johannes Kepler played a key role in the profound changes in human thinking during the scientific revolution. In Kepler's lifetime, religion clashed with religion, religion clashed with science. The old ideas of Ptolemy and Aristotle clashed with the new discoveries of Copernicus and Galileo. The superstition of astrology clashed with the science of astronomy. Kepler reflected the times he lived in. Seen through modern eyes, he had somewhat contradictory ideas. He was an unorthodox Protestant, a follower of Copernicus and Galileo. He was a brilliant mathematician and scientist who discovered that the solar system's planets followed elliptical paths, not circular ones. An astrologer whose horoscopes were sought out as among the best available. Such contradictions were not unusual during the scientific revolution. Isaac Newton, who lived in a later time than Kepler, 1643 to 1727, did not work in the way a modern scientist would. Also, a Protestant with unorthodox views, Newton spent more time investigating the true meaning of the Bible's word and on the pseudoscience of alchemy than he did on mathematics or physics. Johannes Kepler's early life and education. Kepler was born on December the 27th, 1571, in the town of Wilderstadt, which lay in the Holy Roman Empire and is now in Germany. His father, Heinrich Kepler, was a mercenary soldier who abandoned the family when Johannes was 5 years old. His mother, Katrina Goldenmann, was a herbalist and healer who later faced accusations of witchcraft. Kepler showed an early aptitude for mathematics and astronomy. Here you can see two events that inspired a young Kepler to study astronomy: the Great Comet of 1577 and a lunar eclipse in 1580. He attended a local school in Leonberg before moving to a seminary school in Heidelberg. Kepler then entered the University of Tübingen in 1589 on a scholarship, initially studying philosophy and theology. He studied under Burnell, a prominent astronomer who introduced Kepler to Copernican theory. Academic and professional career. In 1594, Kepler became a mathematics teacher at a Protestant school in Graz, Austria. While teaching, he published his first major work, Mysterium Cosmographicum, the Cosmographic Mystery, in 1596, which defended the Copernican system and proposed a model of the universe based on geometric principles. In 1600, Kepler moved to Prague to work with the renowned Danish astronomer Tycho Brahe, who had a wealth of precise astronomical data. After Brahe's death in 1601, Kepler inherited his position as imperial mathematician and access to Brahe's extensive data. Major achievements. Kepler's laws of planetary motion. First law, 1609. Published in Astronomia Nova, New Astronomy. It states that planets orbit the Sun in ellipses, with the Sun at one focus. Second law, 1609. Also in Astronomia Nova. It describes how a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. Kepler's third law, 1619, published in Harmonices Mundi, the harmony of the world. It states that the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. In 1627, Kepler published the Rudolphine tables, which were more accurate astronomical tables for predicting the positions of stars and planets. This work was based on Tycho Brahe's observations and Kepler's own theories. Optical works. Kepler made significant contributions to the field of optics, including the understanding of the human eye and how lenses worked. In 1604 he published Astronomia Pars Optica, the optical part of astronomy, which laid the foundation for the modern theory of lenses and telescopes. His 1611 work, Dioptrics, detailed the properties of light and how it is refracted through lenses. Kepler designed an improved version of the refracting telescope, now known as the Keplerian telescope, which used two convex lenses and provided a wider field of view. Personal life, marriages and family. Kepler married twice. His first wife, Barbara Müller, died in 1611, leaving him with two children. He remarried in 1613 to Susanna Rutinger, with whom he had 6 children, though only 3 survived to adulthood. House of Kepler and Barbara Müller in Gossendorf near Graz. Throughout his life, Kepler faced numerous personal and professional challenges, including financial difficulties, religious conflicts as a Lutheran in a predominantly Catholic environment, and the death of many of his children. Here is an image of Susan Rutinger, Kepler's second wife. Legacy and death. Johannes Kepler died on November 15, 1630, in Regensburg, Germany. He left a lasting legacy in the fields of astronomy, mathematics, and optics. His laws of planetary motion were fundamental to the later work of Isaac Newton and the formulation of the law of universal gravitation. Kepler's contributions to astronomy and science. Kepler's supernova. In 1604, Kepler observed a supernova, now called Kepler's supernova, which challenged the Aristotelian belief in the unchangeability of the heavens. Planetary motion and elliptical orbits. Kepler's discovery that planetary orbits are elliptical rather than circular revolutionized the field of astronomy and provided a more accurate model of the solar system. Keplerian telescope and optics. His design of the Keplerian telescope improved the functionality and power of the telescope, aiding future astronomical observations. Advancements in mathematical astronomy. Kepler's work provided critical advancements in the use of logarithms for simplifying complex calculations in astronomy. Influence on future scientists. Kepler's laws and methods influenced future generations of scientists, including Isaac Newton, who used Kepler's work as a foundation for his own laws of motion and gravitation. Philosophical and theological impact. Harmony of the spheres. Kepler believed in a cosmic harmony and sought to explain the universe in terms of geometric and musical relationships, an idea expressed in his book Harmonices Mundi. Integration of science and faith. Despite facing religious persecution and conflict, Kepler maintained a deep faith and saw his scientific work as a way to understand God's creation. Key publications: Mysterium Cosmographicum, 1596. First major work defending the Copernican system and proposing a geometric model of the universe. Astronomia Nova, 1609. Introduced Kepler's first 2 laws of planetary motion and detailed his astronomical observations and theories. Harmonices Mundi, 1619. Published his 3rd law of planetary motion and explored the harmony of the cosmos. Epitome Astronomia Copernicana, 1618 to 1621. A comprehensive summary of Copernican astronomy, incorporating Kepler's own laws and observations. Impact and recognition. Immediate influence. Kepler's work was not immediately recognized or understood by all his contemporaries, but gradually gained acceptance and acclaim. Long-term legacy. His contributions have had a lasting impact on the fields of astronomy, physics and mathematics. Kepler is remembered as one of the key figures of the scientific revolution, whose work laid the groundwork for modern astronomy. Commemoration. Numerous scientific terms, concepts and celestial bodies have been named in his honor, including Kepler's laws of planetary motion, the Kepler Space Telescope, and lunar and Martian craters. In summary, Johannes Kepler's life was marked by significant scientific achievements that transformed our understanding of the cosmos. His pioneering work in astronomy, optics and mathematics has left an enduring legacy that continues to influence science today. Despite personal and professional challenges, Kepler's dedication to uncovering the laws of nature and his innovative thinking solidified his place as a cornerstone of modern science. Remnant of Kepler's supernova, SN 1634. Thank you again for watching this episode of An Astronomical Life. Goodbye.
Welcome to Space Oddities. In this video we're going to be looking at the story of Pluto and finally asking the question, could it ever be restored to being a planet again? Now, to answer that question we need to understand the series of events that led to Pluto being demoted as a planet in 2006 when it was relegated to the status of a dwarf planet. The story of Pluto, from its discovery to its demotion as a planet and beyond, is quite long, but it's incredibly interesting, so stay with us while we explain how and why Pluto went from planet to dwarf planet. To put the story of Pluto in context, we need to appreciate how the whole question of what a planet actually is has evolved, and how our definition of what a planet is has changed over time. By the end of this video, I hope you will appreciate that the demotion of Pluto was the culmination of a long and complex issue that has persisted for centuries without a resolution, even to this day, and is not as clear-cut as you might think. Well, I'm going to tell you all about that issue and why it matters. To commence our story, we need to start a long way back in time with the ancient Greeks. The term planet comes from the ancient Greeks. They noticed that there were points of light in the heavens that did not wheel around the celestial pole in predictable, graceful arcs as stars did, but instead seemed to follow their own paths across the sky. Sometimes these unwavering points of light, which did not twinkle like stars do, even appeared to move backwards in the sky. They named these celestial objects asteres planetae, meaning wanderers, from where we get the word planet. Until the invention of the telescope, the term planets referred to any of those objects which could be seen with the naked eye, moving against the fixed background of the stars. Thus, the solar system consisted of planets only as far out as Saturn, because those were the only planets visible to the naked eye. Uranus and Neptune could only be seen with the aid of telescopes, so their discovery would have to wait until 1781 and 1846 respectively, although Uranus is allegedly visible to people with exceptionally keen eyesight under perfect conditions. With the discovery of Neptune and Uranus, the solar system expanded to 8 planets. But then, in 1801, the asteroid Ceres was discovered by Giuseppe Piazzi. At just under 1,000 kilometers across, Ceres was considered to be a planet-sized object and was thus classified as a planet. It's not usually visible to the naked eye except under ideal conditions, as its magnitude varies from 6.7 to 9.3. Ceres was the first asteroid to be discovered in the main asteroid belt between Mars and Jupiter. Other asteroids of similar size and shape were later discovered and were likewise classified as planets, so many in fact that by 1851 the solar system consisted, as astronomers viewed it, of the 8 major planets and 15 asteroids, making 23 planets in total. It was clear that many asteroids, as we now refer to them, remained to be discovered. Here are some of the largest asteroids in the solar system. Notice that none of them are perfectly spherical, a fact that became clear as telescopes improved through the latter half of the 19th century. These were obviously very different objects to, say, the Earth or Mars. Many asteroids were also significantly smaller than the major planets, so following a suggestion by Alexander von Humboldt in the 1850s, objects in the main belt between Mars and Jupiter were demoted and reclassified as asteroids. The term asteroid had first been proposed by William Herschel in 1802. In 1841, the term minor planet also appeared as an alternative to the term asteroid. In fact, minor planet remained as an official sub-classification of planets until 1932. So let's just step back at this point and ask the following question. In the mid-19th century, what were the prevailing definitions among astronomers of planets and asteroids? Astronomers defined a planet as orbiting the Sun, spherical and large, whereas an asteroid was orbiting the Sun, possibly spherical, but smaller than a planet. There are some obvious questions here. How large does an object have to be to qualify as a planet? Ceres is so much smaller than the Earth, sure, but the Earth is so much smaller than Jupiter. Where is the cut-off point in terms of size between an asteroid and a planet? Now we can see that the definition of what constitutes a planet was pretty sketchy at most, but it didn't seem to matter. Asteroids were those bodies between Mars and Jupiter. Everything else in the solar system, with the exception of comets, was a planet. Most astronomers didn't really bother themselves too much with the definition of what exactly a planet was. It didn't have much bearing on their work. There was no reason why they should bother themselves with an angels on the head of a pin definition of what a planet was. There were 8 planets and that was that, and exactly how they were defined seemed obvious. But that is not to say that the question of what constitutes a planet was not being discussed. Prominent astronomers of the day added their voices to the discussion. William Herschel opined that a planet is a body which revolves around the Sun in an orbit nearly circular and of a magnitude sufficient to be visible by the naked eye. Well, just a few years later he would discover the planet Uranus, which was not a naked eye object, so his definition was demonstrably wrong. His son John later ruminated on how difficult it was becoming to classify asteroids. He said, "The discovery of these small bodies between Mars and Jupiter has complicated our understanding of what constitutes a planet. Their small size and irregular orbits makes them difficult to categorize." No less an august personage than the Astronomer Royal George Biddell Airy, who held that post from 1835 to 1881, added his voice to the discussion, stating, "The increasing number of minor planets discovered in the region between Mars and Jupiter necessitates a re-evaluation of our criteria for what constitutes a planet." Here was the expression of a dawning realization among astronomers that the question of what exactly constitutes a planet needed a more precise definition. French astronomer Urbain Le Verrier, who predicted the discovery of Neptune, thought the definition of a planet should be defined by its gravitational influence. He wrote, "A planet must exert a significant gravitational influence on its surroundings, distinguishing it from smaller bodies like asteroids." German astronomer Friedrich Wilhelm Bessel expressed the growing realization of the need for a better characterization of planets by opining, "As our observational techniques improve, so too must our definitions adapt to encompass the diversity of celestial bodies we encounter." But all these varying opinions did nothing to change the status quo. Astronomers continued to use imprecise definitions of solar system objects. And then, On January the 1st, 1930, an event occurred which was to have profound impact on the question of what exactly is a planet. On the first day of 1930, Pluto was discovered at the Percival-Lowell Observatory in Arizona by the astronomer Clyde Tombaugh. He had been searching an area of sky where it was predicted that a planet should exist, thanks to observations which seemed to show that Neptune's orbit was being disrupted by the gravitational tug of another body further out. We now know that those observations were erroneous. There was no disruption to Neptune's orbit, and moreover, Pluto could not have been responsible for the observations even if they had been correct. It simply doesn't have enough mass to pull on Neptune in any measurable way. In the light of this, Tombaugh's discovery of Pluto can be seen as pure luck. Pluto is just a pinpoint of light which may never have been discovered were it not for Tombaugh's perseverance, photographic expertise and determination to find the mysterious planet. 2 months later, other astronomers had verified Tombaugh's discovery, and in March 1930 it was announced to the world. The announcement of Pluto's discovery made the front pages around the world, celebrating it quite rightly as a triumphant astronomical discovery. Little was known about this far-off world out beyond the orbit of Neptune because it was just a faint point of light in even the world's biggest telescopes, but that didn't of course stop speculation. The Knickerbocker Press of New York ran an article stating that savants, what you and I might call experts, had estimated that the new world was possibly bigger than Jupiter, perhaps stemming from the need for it to have a lot of mass to be able to affect the orbit of Neptune. It all fit the narrative. The solar system had an additional planet, possibly as big as Jupiter. Tombaugh's own estimate of Pluto's diameter, arrived at shortly after its discovery, was 14,000 kilometers, at least 6 times bigger than it actually is, but of a size which so obviously, for astronomers, identified it as a planet. Now, if you want to register any astronomical claim, like the discovery of a new planet or a new comet, a new asteroid or anything else, you have to report your discovery to an organisation called the International Astronomical Union, or IAU. The organisation had set itself up in 1919 to be the arbiter and certifier of any new astronomical discoveries and could choose to accept or reject them. More importantly, however, the IAU is the body which decides what to name astronomical objects or features on them like craters or mountains, but most importantly it gets to decide how to categorise astronomical objects. The naming of Pluto, however, was not decided by the IAU in a break from convention. It was decided by running a public competition to name the new world, which was won by a British schoolgirl. Not long after its discovery, astronomers worked out what the orbit of Pluto looked like, and it was unlike any other planet in the solar system. Highly elliptical, the orbit is tilted at an angle of 17 degrees relative to the orbits of the other planets, which all orbit in a flat plane. Perhaps most interestingly, Pluto orbits the Sun in the opposite direction to all the other planets. Here was the first indication that Pluto was not like any other planet in the solar system. Estimates of its size had not really changed since its discovery. Earth-sized was still the best guess, but as it remained a mere pinprick of light in even the largest telescopes, its size was extremely difficult to gauge. Estimates of its distance were pretty imprecise too. It's not clear whether Pluto's odd orbit prompted the ringing of any alarm bells among astronomers with regard to how Pluto should be categorised, but it should have done. Pluto was different. It's an outsider. So this is what we see in telescopes, a distant point of light way out beyond Neptune, about which astronomers knew virtually nothing until the 1970s. A world thought to be the size of the Earth, but with much uncertainty. A planet which orbits in an inclined elliptical orbit, travelling in the opposite direction to the other planets, with each orbit taking 248 Earth years. Pluto has not therefore completed even one orbit around the Sun since its discovery. Assumed to be icy or rocky in nature, this strange world kept its secrets out there in the dark on the edge of the solar system. Pluto was an enigma, and one which could be only fully understood by sending a spacecraft there, but there was no appetite for that. But then, in 1978, there was a major discovery. Remember that Pluto is just a point of light in even the world's biggest telescopes, and if you zoom in on it you end up with just a fuzzy ball like the images shown here. There's no surface detail you can see, Pluto's far too far away for that. It's just an indistinct, very roughly circular blob. But these images show something else, something which had not been seen before. Can you spot what it is? James W. Christie made the discovery on June the 22nd, 1978 at the US Naval Observatory in Flagstaff, Arizona. This was only about 6 miles from where Pluto itself was discovered at the Lowell Observatory. Christie was trying to refine Pluto's orbit around the Sun by repeatedly photographing it at maximum zoom, if you like. However, he noticed that images of Pluto were strangely elongated, which you can see here. The blob seemed to move around Pluto as well. The direction of elongation cycled back and forth over 6.39 days, Pluto's rotation period. Searching through their archives of Pluto images taken years before, Christie and colleagues found more cases where Pluto appeared elongated. Additional images confirmed he had discovered the first known moon of Pluto. It received the name Charon from the Greek Charos, meaning fierce or brightness. With half the diameter and 1/8 the mass of Pluto, Charon is a very large moon in comparison to its parent body. Its gravitational influence is such that the barycenter of the Plutonian system, the barycenter meaning the point around which two bodies co-orbit each other, lies outside Pluto, and the two bodies are actually tidally locked to each other, which means that from Pluto you only ever see one face of Charon, and vice versa. This beautiful image of Pluto and Charon was taken in 2015 by NASA's New Horizons spacecraft when it flew through the Plutonian system. It was the first spacecraft to ever visit Pluto. You can see how large Charon is compared to Pluto, half its size. Not long after Charon's discovery, astronomers calculated what its orbit around Pluto told us about the size and mass of each body. The results were surprising. There was no way now that Pluto was the size of the Earth, not even close. Pluto is more the size of an asteroid than a planet. We now know, thanks to discoveries made by the New Horizons spacecraft during its approach to the Plutonian system, that Pluto actually has 5 moons. Here they are in comparison to the size of the Earth. For the next chapter of our story, we need to go back to the year 1951. At that time, astronomers' view of the solar system divided it into 2 main zones. The inner zone, comprising the rocky or terrestrial planets, that is to say Mercury, Venus, Earth and Mars, and the outer zone, comprising the gas giants Jupiter, Saturn, Uranus and Neptune. Between the two is the asteroid belt. However, in 1951, Dutch astronomer Gerard Kuiper proposed a 3rd zone, which became known as the Kuiper Belt. This zone, said Kuiper, is a reservoir of comets, thus explaining where many comets came from. At the time this made some sort of sense because we didn't know the origin of many comets, and especially not long period comets. He described the eponymous belt as a disk of icy bodies, i.e. comets, beyond Pluto. Kuiper, however, thought that apart from comets the belt would be empty, and so it went for the next 40 years. But then in 1992 a team who had been surveying the Kuiper belt made a discovery, and it wasn't a comet. David Dewitt and Jane Liu found the first Kuiper belt object after 5 years of astronomical observations. It was designated 1992 QB1, later changed to Albion. Albion's between 108 and 167 kilometers in diameter and orbits the Sun every 296 Earth years. Its distance from the Sun varies between 41 astronomical units, or AU, 1 AU is the distance from the Earth to the Sun, and as far as 47.7 AU. It has a reddish colour. But the important thing is that this was a body of type unknown but too big to be a comet, in a zone of the solar system where there was not meant to be anything except comets. This was, to coin a cliché, a game changer, because where there was one object there were almost certainly more. and it wasn't long until many more were discovered, so many in fact that it's now estimated that the Kuiper belt contains more than 100,000 icy bodies. The belt is the last outpost of the solar system. Beyond that, far beyond that, is the Oort cloud, a huge reservoir of long-period comets, perhaps trillions of them. We're pretty sure that the Oort cloud exists, and that is where long-period comets originate rather than from the Kuiper belt, but its existence is nonetheless still hypothetical. With the discovery of the first Kuiper belt object, and the reasonable expectation that more would follow, attention turned to the question of exactly what these objects were and how they orbited the Sun. This was also of growing importance because, due to various reasons, the Kuiper belt was said to begin at 30 astronomical units from the Sun, that is 30 times the Earth-Sun distance, but Pluto, back in the 90s, was 39 AU from the Sun. In other words, Pluto is a Kuiper belt object. It's the closest one to us, but definitely a denizen of that outer solar system zone. After more icy objects were discovered in the Kuiper belt, didn't it make more sense to devise a special category for them? The American astronomer Frederick C. Leonard had pondered the existence of such a population of objects not long after Pluto was discovered in 1930. He wondered if it was, quote, likely that in Pluto there has come to light the first of a series of ultra-Neptunian objects, the remaining members of which still await discovery, but which are destined eventually to be detected, unquote. Notice his contemplation that Pluto was a member of a completely new class of objects. As more and more of the population that Leonard had pondered were discovered, astronomers realized the necessity of coming up with a name to refer to them. So they did. The name was Trans-Neptunian Objects, or TNOs. 1992 was a momentous year for astronomical discoveries. As well as Albion, astronomers also detected the first exoplanet, in other words, a planet orbiting another star. It may seem obvious that other stars have planets too, but it was by no means a given back then. The discovery of the first exoplanet, actually two were discovered at the same time, is relevant to our story, but we'll come back to that later. A year later, and another term was coined. This was the Plutino. 1993 saw the discovery of a Kuiper belt object that had roughly the same orbit as Pluto and had the same orbital resonance with Neptune, 2 to 3. This means that for every 2 orbits around the Sun completed by the object, Neptune completes 3. These objects were named Plutinos because guess which was the first ever discovered? Yes, Pluto. Plutinos form the inner part of the Kuiper belt and represent a quarter of its known objects. They are a class of object all of its own. But the question was, of course, are they planets? In the years that followed, more TNOs were discovered. But then, in 2003, one was discovered which really upset the proverbial apple cart. Its name is Eris, after the Greco-Roman god of strife and discord. Its name could not have been chosen more appropriately. You see, Eris appeared to be slightly bigger than Pluto. NASA immediately described Eris as the solar system's 10th planet. Just how many planets was the solar system going to end up with? If there were thousands of TNOs awaiting discovery which are comparable in size to Pluto and Eris, would the solar system therefore include thousands of planets? When it was also discovered that Eris has its own moon, it muddied the waters even further. Eventually, incidentally, it was found that initial estimates of Eris' size had been wrong and that Eris is actually a tiny bit smaller than Pluto, although it does have more mass. Well, I hope you can see that the situation was getting complicated. There was a growing call from astronomers and planetary scientists to, once and for all, define exactly what a planet is and what it is not. Moreover, since astronomers were finding more and more exoplanets, the need for a rigid classification of the bodies orbiting a star was becoming ever more pressing. If we cannot adequately characterize the objects in our own solar system, what chance would we have of using the correct classifications when talking about other star systems? Especially when nobody knew if we would discover completely unknown types of objects orbiting other stars. Rumblings in the astronomical community continued, and the matter finally came to a head in 2006 in Prague, capital of the Czech Republic. There, the IAU was to hold its 26th General Assembly. Remember, the IAU is responsible for approving names, categories and features of astronomical bodies. The issue of what constitutes a planet was to be discussed. The objective was to come up with a new and definitive definition of a planet. If Pluto matched the definition, it would remain as a planet. If not, then some other category would need to be bestowed upon it and objects like it. A new definition of a planet was proposed to the Assembly by astronomer Mike Brown, Professor of Planetary Astronomy at the California Institute of Technology. Brown was the person who had discovered Eris, which was, initially, as you will recall, thought to be larger than Pluto. Brown no doubt saw the need for changes after his discovery of Eris and wanted to be the person to push for those changes. Supporting his proposal was the president of the IAU, Catherine Cesarski. Despite later writing a book entitled How I Killed Pluto and Why It Had It Coming, Brown has always maintained that his intention was not to strip Pluto of its planetary status. That would merely be a byproduct of changes to the definition of a planet. He merely wanted people to recognise that the solar system had changed and new definitions were needed, and the public needed to be educated a little more about what was really out there at the edge of the solar system. Let's examine Mike Brown and Catherine Cesarski's proposed new definition of a planet. Brown's proposed definition of a planet comprised just 3 criteria. Let's take them in turn. 1. A planet is a celestial body which orbits the Sun. Well, that sounds reasonable, no? That might be many people's definition full stop of what a planet is. Nothing controversial there. But hang on, he says the Sun orbits the Sun. So what about those exoplanets orbiting other stars, of which more than 5,000 have so far been discovered? Are they not planets after all? Does this definition fail at the first hurdle? Well, that's not a good start, but anyway, so far Pluto hangs on to its planetary status because it does orbit the Sun, yes. 2. It is almost spherical. Sounds okay. All the major planets are mostly spherical. Pluto is mostly spherical too, so survives being a planet. So far so good. 3. It has cleared the neighbourhood around its orbit. This means that it has become gravitationally dominant and there are no other bodies of comparable size other than its natural satellites or those otherwise under its gravitational influence in its vicinity in space. And here is where Pluto lost its planetary status. Pluto has not cleared its orbit of other bodies. The other Plutinos that we discussed orbit in its vicinity. But note this, the phrases cleared the neighbourhood and in its vicinity are imprecise and undefined. What exactly constitutes a neighbourhood? How close do other objects have to be included in Pluto's neighbourhood? Similarly, in its vicinity, how far does Pluto's vicinity extend? 1,000,000 miles? 10? 50? 100? These terms are not the precise ones we expect from astronomy, where precision is everything. There's no room in science for ambiguity after all. Also, clearing the neighbourhood has more to do with the body's mass, not the distance to other objects around it. Pluto's mass is so low, in fact, that it's impossible for its gravity to have cleared out its orbit. Surely some reference to an object's mass should have been included in this criterion. We can see that Brown's proposal, on which the final vote was to be taken on the last day of the IAU Assembly, was vague and ambiguous. It was certainly far from an ideal definition of a planet. It fell at the first hurdle by insisting that a planet orbits the Sun, as if extrasolar planets don't exist. It failed to quantitatively define the terms neighbourhood and vicinity. Surely the vote would not go in favour of Brown's proposal. And so we finally come to the vote. It was the closing ceremony of the IAU 2006 Assembly. 2,500 astronomers, representing 10,000 professional astronomers around the world, had attended the assembly. It was not usually the case at IAU assemblies that most delegates attended the closing ceremony on the last day. Many, in fact, had left the day before. So many, in fact, that when the time came for the vote, just 424 delegates remained at the closing ceremony when the vote on Brown's proposal was due to take place. Brown's moment had come. The vote was taken and it was carried. Suddenly there was a new definition of a planet, and poor Pluto was unceremoniously dumped from its planetary status. The solar system now had 8 planets, not 9. After 76 years, we finally knew what Pluto was not. It was not a planet. So, what was it? Well, after the vote, the remaining delegates agreed on a new classification of solar system objects, dwarf planets. This new category included not just Pluto, but the main belt asteroid series, plus the Kuiper belt objects Eris, Haumea and Makemake, a total of 5 dwarf planets. Hurriedly, some delegates tried to recognise dwarf planets as actual planets, but this was defeated. Had the vote been taken before most of the delegates had left, would the vote still have been carried? Very probably not, although of course we'll never know. We can surmise that the vote would have gone against Brown due to the immediate and fierce reaction from astronomers when they learned that their own professional body, the IAU, had just declared that Pluto was not a planet anymore. They were not, to put it mildly, happy. Did Brown and Ciesielski intentionally wait until the room was nearly empty to hold the vote so it was more likely to succeed? Perhaps. The timing of the vote does seem as if it were premeditated. In light of this, can we say that Brown and Ciesielski fixed the vote? Maybe. If they had wanted forthright and honest debate, if they had wanted to hear the opinions of the world's astronomers, not just those represented by the 424 remaining delegates, they would have taken the vote sooner in the assembly. This can be argued about, of course, but one thing was certain: neither Brown nor Ciesielski could have been prepared for the global furore they had just unleashed. Global reaction ranged from sheer disbelief to outright anger. It seemed such an arbitrary, hurried decision. Textbooks would have to be rewritten, although of course this does happen on a continuous basis with astronomy. Children in schools would now learn about a solar system comprising 8, not 9 planets. Pluto was relegated to a dwarf planet. Still a little bit of a planet, obviously, but of definite inferior status to actual planets. Brown had got his way and killed Pluto. While he maintains that was not his intent, that's what happened, and it was an inevitable result of his emphasised definition of a planet that had been agreed upon by a small number of delegates at the IAU assembly. One astronomer said afterwards, "I'm embarrassed for astronomy. Fewer than 5% of the world's astronomers voted." This embarrassment was shared across the globe by professional astronomers. The media went wild, scenting blood. Nothing sells like controversy after all. The airwaves and the internet were filled with diatribes against the decision. Demoting Pluto as a planet has been probably the most controversial move in the history of astronomy, with entrenched opinions on both sides. There was literal global outrage. In the US, several state governments publicly denounced the demotion. Now, there weren't exactly riots in the streets. Oh, wouldn't it be wonderful if people felt so passionately about their universe? But the level of public anger was immense. Now, there was a minority of astronomers who thought it was a good move, citing the reasons we've discussed, but most seem to be totally against the idea. Many still are. But why do so many people want Pluto to be a planet when, as we have seen, there is little justification for putting it in the same category as, say, the Earth or Jupiter? I think a lot of it has to do with nostalgia. People want things the way it was when they were young, when the solar system had 9 planets, when you could depend on things, when things didn't change. I firmly believe that a lot of the protest about Pluto losing its planet status is simply nostalgia for lost youth. This image is of a book from my own collection. It was published in the early 1950s. Like many other people, I grew up with books like this, marvelling at the endless possibilities of space exploration. Yes, of course this book had Pluto as a planet, but it also had Jupiter possessing 12 moons and Saturn 9. Well, we now know that Jupiter, at last count anyway, has 95 moons and Saturn an astonishing 146. The point is that finding more moons around planets has been accepted without protest. The solar system has changed almost beyond recognition from the one portrayed in Adventures in Space. Yet nobody, as far as I'm aware, has ever written angry letters to newspapers when new moons have been discovered. So why protest so strongly about Pluto, whose demotion from planet to dwarf planet can be seen as a natural process resulting from astronomers learning more about the solar system? So let us now at last return to ask the question we posed at the beginning. Is there any possibility that Pluto will ever regain its planetary status? Well, I think the best we can say is that it's highly unlikely, but not out of the question altogether. You see, scrutiny has recently returned to those criteria approved at the 2006 IAU Assembly. So what's happened? Dr. Jean-Luc Margot, a professor in the Department of Earth, Planetary and Space Sciences at the University of California in Los Angeles, and his colleagues from the US and Canada, have recently completed a study which proposes yet again a new definition of a planet. It's been published in the Planetary Science Journal. It recognizes the deficiencies of the 2006 definition while seeking to establish a more natural, logical way of defining what a planet is. Moreover, it does not seek to limit the number of planets in a star system. If, under the new definition, a star system has 50 planets, then so be it. Let's have a look at the proposed definition. The new proposal has again three criteria. Number 1, a planet orbits one or more stars, brown dwarfs or stellar remnants. This replaces the reference to a planet orbiting the Sun, as it now includes any stars, brown dwarfs or stellar remnants, things like neutron stars or pulsars. Don't forget that the first two exoplanets ever discovered were found orbiting a pulsar. Number 2, a planet has more mass than 10 to the power of 23 kilograms. This criterion imposes a lower mass limit for a planet. But why 10 to the power of 23 kilograms? Well, that's considered to be the minimum mass a planet needs to have in order to pull itself into a spherical shape and clear its orbit of other objects. At a stroke, it replaces two of the previous criteria. And number 3, a planet is less massive than 13 Jupiter masses, that is 2.5 times 10 to the power of 28 kilograms. Now this criterion sets an upper mass limit for a planet because anything with more mass, more than 13 times that of Jupiter, is considered to be a brown dwarf, a sort of intermediate stage in terms of mass between a planet and a star. These new criteria, which obviously have to be voted on at an IAU assembly, Professor Margot wants to put it to the vote in 2027, seem eminently sensible, less ambiguous and definitely more specific in terms of numbers than the 2006 definition. Professor Margot spoke to Universe Today and he had this to say. Basically, he's saying that the upper and mass limits in his proposal lead naturally to the solar system with C, with 8 planets. Pluto does not have the minimum mass. In addition, he proposes that instead of a planet having cleared its orbit, it needs to do so within a specific time frame, which again will depend on its mass. By adopting a system which defines a planet by its orbital element and its mass, the whole business of defining a planet becomes much simpler and can be applied to any star systems. And with the rate at which exoplanets are being discovered, we do need a far more rigid, easy to apply system to classify objects around other stars. So where does this leave Pluto? Under the new proposal, Pluto is not defined as a planet because its mass falls below the lower limit. But that's not to say that at some point in the future, new discoveries may necessitate the redefining of a planet again, and Pluto might be restored. It seems unlikely now, but that may not always be the case. Astronomy is constantly changing, ideas change. So for all you lovers of Pluto as a planet, don't give up hope. The important thing to remember is that just because a body like Pluto is currently considered a minor player in the solar system, that's not to say in any way that it is less worthy of study. When NASA's New Horizons probe flew by Pluto in 2015, it discovered a dynamic, changing, enigmatic world with its own marvels and scientific challenges. It's an amazing object in the solar system which needs to be revisited. Ignore the fact that it's now a lowly dwarf planet. Pluto is one of the most interesting objects in the solar system, whose origins and evolution will take many years to understand. After all, what's in a name? Well, we hope you have enjoyed this video about Pluto and that you will subscribe to our channel if you haven't already. We create videos like this all the time. Don't forget to watch our Tuesday live streams when we bring you the latest astronomy and space exploration news, discussions, special guests and a lot more. If it's happening in space, it's happening on Space Oddities. Thank you so much for watching, and until next time, goodbye.
Welcome to Space Oddities and this episode of An Astronomical Life. The life we are looking at today is Dame Susan Jocelyn Bell Burnell. Early life and education. Susan Jocelyn Bell was born the 15th of July 1943 in Lurgan, Northern Ireland. Her parents were George and M. Allison Bell. Her father was an architect who helped design the Armagh Planetarium. Jocelyn's early interest in astronomy. Her father's involvement in the planetarium sparked her interest in astronomy. He provided books on the subject. One author in particular inspired Jocelyn's interest in astronomy, Fred Hoyle. He would later, on more than one occasion, play small parts in Jocelyn's future. Jocelyn attended Lurgan College, where she faced gender barriers, initially not allowed to study science. After failing her 11 plus, Jocelyn's parents sent her to the Mount School, a Quaker boarding school in York where she excelled in physics. There she was favourably impressed by her physics teacher, Mr. Tillott, and stated, "You do not have to learn lots and lots of facts. You just learn a few key things, and then you can apply and build and develop from those." He was a really good teacher and showed me actually how easy physics was. After York, Jocelyn moved to the University of Glasgow, where she earned a Bachelor of Science degree in physics in 1965. Next for Jocelyn was the University of Cambridge, where she pursued a PhD in radio astronomy under the supervision of Anthony Hewish. Discovery of pulsars. Jocelyn focused on constructing and utilizing a large radio telescope, the Interplanetary Scintillation Array just outside Cambridge, to study quasars. The remains of the Interplanetary Scintillation Array just outside Cambridge still exist today. Data collected by the Interplanetary Scintillation Array was recorded on a tracing machine similar to the image on the left. Every day Jocelyn collected reams of data, come rain or shine, and returned to her student accommodation where she would then analyze the data. Observations. Jocelyn detected a series of unexpected radio pulses on the 28th of November 1967. Jocelyn described this as a little bit of scruff in the trace. Jocelyn realized she had seen this little bit of scruff before. Going back through the data, she found a second signal on the 6th of August 1967. The signal was repeating. Jocelyn reported her findings to her mentor, James Hewish, who in turn notified his superior, Martin Ryle. Initial skepticism. The pulses were nicknamed LGM for Little Green Men, due to the possibility of extraterrestrial origins. LGM as a nickname would later prove to be a problem. Before the nature of the signal was determined, the researchers, Burnell, and her PhD supervisor, Anthony Hewish, considered the possibility of extraterrestrial life. He said, "We did not really believe that we had picked up signals from another civilization, but obviously the idea had crossed our minds, and we had no proof that it was an entirely natural radio emission. It's an interesting problem. If one thinks one may have detected life elsewhere in the universe, how does one announce the results responsibly? Who does one tell first?" The signal was confirmed. They had found and identified a repeating signal which led to the conclusion of a new type of celestial object. But what was this object? Astrophysicists, including Fred Hoyle and Thomas Gold, posited that the new discovery were from the remains of a collapsed star called a neutron star. The signal were confirmed to be from a rapidly rotating neutron star, later termed a pulsar. Jocelyn Bell co-authored a paper in 1968 detailing the discovery with her supervisor Anthony Hewish and other colleagues. A public announcement was made of the discovery in February 1968. Jocelyn later related how the media was covering the discovery of pulsars, with the interviews taking a standard discussing format. Hewish would be asked questions on astrophysics, and she would be the human interest part, asked about her vital statistics, how many boyfriends she had, what colour is her hair, and asked to undo some buttons for the photographs. Recognition and Nobel controversy. The impact. The discovery of pulsars was a groundbreaking announcement in astrophysics. Nobel Prize. In 1974, Anthony Hewish and Martin Ryle were awarded the Nobel Prize in Physics. Burnell was not included, leading to widespread debate and criticism regarding the exclusion of her critical contributions. Some even today refer to 1974 as the Nobel Prize in Physics. At the time, one of the loudest voices in support of Jocelyn Bell Burnell was fellow astronomer Fred Hoyle, who severely criticized the Nobel Committee for Bell's omission. It is thought this episode contributed to Hoyle being overlooked for a Nobel Prize in 1983. On this episode of the Nobel Prize controversy, Jocelyn later reflected. She said, "First, demarcation disputes between supervisor and student are always difficult, probably impossible to resolve. Secondly, it is the supervisor who has the final responsibility for the success or failure of the project. We hear of cases where a supervisor blames his student for a failure, but we know that it is largely the fault of the supervisor. It seems only fair to me that he should benefit from the successes too. Thirdly, I believe it would demean the Nobel Prizes if they were awarded to research students, except in very exceptional circumstances, and I do not believe this is one of them. Finally, I am not myself upset about it. After all, I'm in good company, am I not?" So, what is a pulsar? Definition. A pulsar is a highly magnetized rotating neutron star that emits beams of electromagnetic radiation. Formation. Originates from the remnants of a supernova explosion. Rotation. spins rapidly with periods ranging from milliseconds to a few seconds. Emissions: emits beams of radio waves, X-rays or gamma rays. Lighthouse effect: the beams sweep across space and, if aligned with Earth, are detected as pulsating signals. Magnetic field: extremely strong, influencing the pulsar's emission mechanisms. Significance: used in astrophysics to study extreme states of matter, gravitational waves and space-time. Acknowledgements: despite the controversy, Jocelyn received numerous accolades, including the Albert A. Michelson Medal, the J. Robert Oppenheimer Memorial Prize, and the Herschel Medal. In 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics. Career and contributions. Research positions. Jocelyn worked at the University of Southampton, University College London and the Royal Observatory Edinburgh. Focused on gamma-ray astronomy, infrared astronomy and the emission of X-rays from neutron stars. Academic roles. Held various teaching positions at prestigious institutions. Appointed as Professor of Physics at the Open University. Became a visiting professor at Oxford University and later the Chancellor of the University of Dundee. Leadership roles. Jocelyn became President of the Royal Astronomical Society, the President of the Institute of Physics, and the President of the Royal Society of Edinburgh. Advocacy and legacy. Promotion of women in science. Jocelyn actively campaigns for greater inclusion and support for women in STEM fields. Personal experiences. Frequently shared her own experiences with gender discrimination in her career. Philanthropy. Donated her Breakthrough Prize money to fund scholarships for women, underrepresented minorities and refugees studying physics. Continued engagement. Jocelyn remains an active figure in the scientific community, participating in lectures, conferences and public outreach. Advocates for education and the public understanding of science. Honours. Numerous honorary degrees and fellowships from leading universities and scientific societies. Continues to be a role model and an inspiration for aspiring scientists, particularly women and minorities in physics and astronomy. Selected publications and works. Pulsars and neutron stars. Jocelyn authored and co-authored several important papers on the nature and properties of pulsars. Books and articles. Contributed to various scientific publications and books, sharing insights on her discoveries and the broader field of astrophysics. Educational contributions. Involved in the development and educational resources and curriculum for teaching physics and astronomy. These are just two of the titles that Jocelyn was involved with. Influence on astronomy and physics. Pioneering work. Her discovery of pulsars has made a profound and lasting impact on the field of astrophysics. Inspirational figure. Recognized as a trailblazer for women in science and an advocate for diversity and inclusion in the scientific community. Enduring legacy. Jocelyn Bell Burnell's life and work continue to inspire and influence the next generation of scientists, contributing to the advancements in our understanding of the universe. Key personal qualities. Resilience. Jocelyn overcame significant barriers and challenges in her career, maintaining a commitment to her scientific pursuits. Humanity. Consistently acknowledged the collaborative nature of scientific research and the contributions of her colleagues. Mentorship. Played a significant role in mentoring young scientists and fostering an inclusive academic environment. Welcome to Space Oddities and An Astronomical Life. Fred Hoyle, 1915 to 2001. Fred Hoyle proved that the great majority of natural elements in the periodic table were made inside stars and distributed through space by supernova explosions. He also coined the phrase Big Bang, while strenuously denying that there had ever been one. He argued for an expanding steady-state universe with no beginning or end. A controversial, often outspoken scientist, he never received a Nobel Prize, even though his work on the creation of chemical elements undoubtedly merited one. He delighted in taking dissenting positions on many of science's big questions. He argued that the physical and chemical properties of the universe had been intelligently designed, and that life on Earth had been seeded from space. Early life and education. Fred Hoyle was born on June the 24th, 1915, in Bingley, Yorkshire, England. His father, Ben Hoyle, was a wool merchant, and his mother, Mabel, was a teacher, so had a deep interest in education. Hoyle attended Bingley Grammar School, where he developed a strong interest in science, especially astronomy. In 1933, Hoyle enrolled in Emmanuel College, Cambridge, to study mathematics. He later shifted his focus to astrophysics. During World War II, Hoyle worked with the Admiralty on radar development, a crucial technology for the war effort. His work during the war introduced him to other significant scientists, including Hermann Bondi and Thomas Gold. After the war, Hoyle returned to Cambridge and became a lecturer in mathematics. The steady-state theory. Alongside Hermann Bondi and Thomas Gold, Hoyle developed the steady-state theory of the universe in 1948, which proposed that the universe is eternal and unchanging on a large scale. One of the key ideas is that matter is continuously created to keep the universe's density constant despite its expansion. Rejection of the Big Bang. Hoyle was a vocal critic of the Big Bang theory, famously coining the term Big Bang in a radio broadcast as a term of derision. Carbon-12 formation. His prediction of the resonance level in the carbon-12 nucleus, which was crucial for the synthesis of carbon in stars, was confirmed experimentally and is considered one of his greatest achievements. Nuclear synthesis. Hoyle made groundbreaking contributions to the understanding of how elements are formed in stars. Hoyle, in 1957, along with his co-workers Margaret Burbidge, Geoffrey Burbidge and William A. Fowler, published one of the most famous papers in the history of astrophysics, Synthesis of the Elements in the Stars, informally entitled B2FH paper, after the surnames of its authors, Burbidge, Fowler and Hoyle. Later career and controversies. Hoyle played a pivotal role in founding the Institute of Astronomy at Cambridge in 1967 and served as its first director. He resigned from his post in Cambridge in 1972, partly due to disagreements over university policies and funding for scientific research. Contribution to other scientific fields. Cosmology and astrobiology. Hoyle was an early advocate for the idea that life could be widespread in the universe and that interstellar dust could be composed of organic compounds. Panspermia hypothesis. He supported and advanced the panspermia hypothesis, which suggests that life on Earth may have been seeded from space. Viruses from space. Hoyle, along with Chandra Vikramasinghe, proposed that viruses and bacteria from space could be responsible for epidemics on Earth. Writing and public engagement. Popular science books. Hoyle was an adept science communicator and wrote several popular science books including The Nature of the Universe in 1950 and The Frontiers of Astronomy in 1955, and also Our Place in the Cosmos. As well as his science book, he also wrote science fiction novels, most notably The Black Cloud in 1957, which explores the impact of a giant interstellar cloud passing through the solar system. Hoyle also reached a wider audience through his BBC radio broadcasts, where he explained complex scientific ideas in an accessible manner. Recognition and awards. He was elected a Fellow of the Royal Society in 1957. Hoyle received the Royal Medal in 1974 for his work in theoretical physics and cosmology. He was also knighted in 1972 for his contributions to science. Gold Medal of the Royal Astronomical Society. Hoyle was awarded this prestigious medal in 1968. Throughout his career, Hoyle received numerous other awards and honorary degrees for his contributions to science and public understanding of science. Controversial views and later years. Rejection of the Big Bang. Hoyle continued to reject the Big Bang theory despite increasing evidence supporting it, which isolated him from much of the mainstream scientific community. Viruses from space theory. His belief in the panspermia hypothesis and that viruses could come from space was also controversial and not widely accepted. Climate change skepticism. In his later years, Hoyle was skeptical of the mainstream views on climate change, which further distanced him from the scientific community. Personal life and legacy. Hoyle married Barbara Clark in 1939, and they had two children, Jethry and Elizabeth. Hoyle passed away on August 20th, 2001, in Bournemouth, England. Hoyle's contribution to our understanding of the universe, particularly in the field of nuclear synthesis, remains highly influential. His advocacy for ideas outside the mainstream highlights the importance of challenging established scientific paradigms, even if not all such challenges prove correct. A quick summary of Hoyle's major works. Scientific books. The Nature of the Universe, 1950. Frontiers of Astronomy, 1955. Galaxies, Nuclei and Quasars, 1965. The Intelligent Universe, 1983. scientific papers. Numerous papers on stellar nuclear synthesis, the steady-state theory, and other astronomical phenomena. Science fiction books. The Black Cloud, 1957. October the 1st is Too Late, 1966. A for Andromeda, 1962, co-written with John Elliott. Hoyle's influence on modern science. Stellar nuclear synthesis. Hoyle's work in this area remains foundational, explaining the formation of heavy elements in stars. Popularizing science. Through his books and broadcasts, Hoyle inspired many to take an interest in astronomy and cosmology. Steady-state theory. Although ultimately disproven, the steady-state theory spurred significant research and debate, contributing to a deeper understanding of cosmology. Final thoughts. Iconoclast. Hoyle's career was marked by his willingness to challenge established ideas and propose bold theories. Scientific contributions. Despite some of his more controversial views, his contributions to our understanding of the universe are undeniable and continue to be celebrated in the scientific community. Climate change skepticism. In his later years, Hoyle was skeptical of the mainstream views on climate change, which further distanced him from the scientific community. Nobel Prize controversy. In 1983, William A. Fowler received a half share of the Nobel Prize in Physics for his theoretical and experimental studies of the nuclear reactions of importance in the formation of the chemical elements in the universe. Hoyle received no prize. Fowler himself acknowledged Hoyle as the pioneer of stellar nuclear synthesis. One of the B2FH paper authors, Geoffrey Burbridge, wrote in 2008, Hoyle should have been awarded a Nobel Prize for this and other work. On the basis of my private correspondence, I believe that a major reason for his exclusion was that W.A. Fowler was wrongly believed to be the leader of this group. Other theories about why Hoyle received no prize include 1. His criticism of the Nobel Committee for awarding Anthony Hewish a share of the 1974 Nobel Prize in Physics for the discovery of pulsars, but making no award to his research student Jocelyn Burnell, who actually made the discovery. 2. His persistence in championing the steady-state universe rather than accepting mainstream Big Bang universe. His support for unorthodox ideas such as panspermia. The support for unorthodox ideas argument could also have been used to prevent Linus Pauling getting the Chemistry Nobel Prize, but fortunately for Pauling, his unorthodox ideas came after he had been awarded the prize. I hope you enjoyed this brief introduction to Sir Fred Hoyle, 1915 to 2001, and thank you again for watching Space Oddities.